Good morning. This is our 25th lecture on statistical mechanics, and we are busy with quantum statistics. Today we will see the equation of state of an ideal Fermi gas. Ideal Fermi gas is constituted by non-interacting Fermi particles, fermions. These Fermi particles have half integral spin, They obey Pauli's exclusion principle. They are represented by antisymmetric wave functions. So these particles are electrons, protons, etc. The equation of state for an ideal Fermi gas may be obtained by eliminating Z from the equation which we have derived earlier. P by kT equal to 4 pi by h cube integral 0 to infinity p square log 1 plus z e to the power minus beta epsilon, or beta p square by 2m we can write, into dp, and n equal to 4 pi by h cube integral 0 to infinity p square dp divided by z to the power minus 1 e to the power beta p square by 2m plus 1, where the small n is particle density, that is n by v. This second equation can also be written as n lambda cube equal to f 3 by 2z, where f 3 by 2z is the Fermi function and n is n by v, and f 3 by 2z is equal to 4 by root pi integral 0 to infinity x square dx divided by z to the power minus 1 e to the power x square plus 1. We shall consider two special cases one by one. First case 1, is when we have the gas at high temperature and low density, low particle density. So T is high and n, small n, is lower, which means the condition is that n lambda cube is very small compared to 1. And we can understand from here that the treatment that is going to be given to the system is that of classical statistics, or the system will behave like a collection of classical ideal gas. In this case, Z is small and the average interparticle separation is large compared to the thermal wavelength. So in this case, we would not expect the quantum effects to be appreciable. So for small z, we have already shown that n lambda cube is equal to z minus z square divided by 2 to the power 3 by 2 and so on. We have seen that if you take up to first term only, n lambda cube becomes equal to z, but z is e to the power alpha and alpha is mu by kt, so that is e to the power mu by kt. So from here, because z is e to the power alpha, we get e to the power alpha equal to n is capital N by v, and for lambda cube we can write h cube divided by 2 pi m kt to the power 3 by 2. So from here we get n equal to e to the power alpha v 2 pi m kt to the power 3 by 2 divided by h cube. This relation leads us to believe that NP, that is distribution function, is given by e to the power alpha into e to the power minus beta epsilon p, where p is the state, that is pth state, energy is epsilon p, which is the Maxwell-Boltzmann distribution function. As e to the power alpha is z and z is n lambda cube, this can also be written as np equal to n lambda cube e to the power minus beta epsilon p which is the average occupation number for Maxwell-Boltzmann gas. For the first approximation, if we go up to second term, we obtain n lambda cube equal to z minus z square divided by 2 to the power 3 by 2, and that can be written as n lambda. For z we can write z equal to, you see, n lambda cube minus, rather plus, z square by 2 to the power 3 by 2. For the approximation, z can be taken as n lambda cube. So we write n lambda cube whole square divided by 2 to the power 3 by 2. So z equal to n lambda cube into 1 plus n lambda cube divided by 2 to the power 3 by 2. We also had P by kt equal to 1 by lambda cube 8 by 3 root pi integral 0 to infinity x4 dx divided by z to the power minus 1 e to the power x square plus 1, and that was P lambda cube divided by kt, and this integral with 8 by 3 root pi was z. For Fermi gas, with this plus over here, we had minus z square divided by 2 to the power 5 by 2 and plus z cube divided by 3 to the power 5 by 2 and so on. So with this value of z and this equation, we can write equation of state as P lambda cube by kt equal to, now for z we are substituting from here, n lambda cube plus n lambda cube whole square divided by 2 to the power 3 by 2, that is z, minus n lambda cube plus n lambda cube whole square divided by 2 to the power 3 by 2 whole square divided by 2 to the power, rather, yes, 2 to the power 5 by 2. So we have P lambda cube by kt equal to n lambda cube plus n lambda cube whole square divided by 2 to the power 3 by 2 minus n lambda cube whole square divided by 2 to the power 5 by 2 plus higher order terms of n lambda cube, which we will neglect. And from here we obtain n lambda cube plus n lambda cube whole square divided by 2 to the power 5 by 2. And from here we obtain P by nkt equal to 1 plus n lambda cube divided by 2 to the power 5 by 2. So that is the equation of state for an ideal Fermi gas when the temperature is high. And we are taking first approximation, which means we are going up to the second term in this equation as well as in this equation also. So these two equations, when we are going up to second term, that is the first approximation, then in that case we get the result which shows that for the same particle density and temperature as an ideal Boltzmann gas, the pressure exerted by an ideal Fermi gas is greater than that in the case of the ideal classical gas. This equation is in the form of a virial expansion. We have already mentioned that the corrections to the ideal Boltzmann gas law are not due to presence of any repulsive molecular interaction, but due to the quantum effects. Obviously, when T becomes sufficiently high so that lambda cube tends to 0, this will be reduced to the classical ideal gas P by nkt is equal to 1. So it is easy to understand that all other thermodynamic functions will reduce to those for a classical ideal gas along with small corrections. Let's take the second case now, case 2. This is when we have low temperature and high density, high particle density and low temperature. That means n lambda cube is very large compared to 1. This is the case where quantum effects, in particular Pauli exclusion principle, are expected to be appreciable, as now the average de Broglie wavelength is much larger than the average interparticle separation. When temperature becomes very low, the average de Broglie wavelength is much larger than the average interparticle separation, so the overlapping of wave function starts to take place. This is the case where Z is large, and when Z is large, an asymptotic expansion may be found through a method which is due to Sommerfeld. This method is due to Sommerfeld. We will follow that method. So let nu be equal to log Z, or Z is equal to e to the power nu. Now this f 3 by 2z that we know is 4 by root pi integral 0 to infinity x square dx divided by z to the power minus 1 e to the power x square plus 1. Let y is equal to x square, and then f 3 by 2z will be 4 by root pi integral 0 to infinity. Now for x square we put y. For dx we get dy equal to 2x dx. So dx is half 1 by x dy, but x is root y. So we get 1 by 2 root y dy. So for dx we substitute here 1 by 2 root y, so we'll get root y here, dy divided by z to the power minus 1 e to the power y plus 1. But z is e to the power nu, so we can again write this as 2 by root pi integral root y dy divided by e to the power y minus nu plus 1 integrated from 0 to infinity. Let's integrate this partially, and then we will get 2 by root pi outside. Let's take 1 by e to the power y minus nu plus 1 as the first function, and second function is root y, which will be integrated 2 by 3 y to the power 3 by 2, and this limit is from 0 to infinity, minus 2 by 3 integral 0 to infinity y to the power 3 by 2. Now we differentiate the first function, so we will get a minus 1, and in the denominator e to the power y minus nu plus 1 whole square, and when we differentiate e to the power y minus nu, we obtain e to the power y minus nu and dy. Now this will give us 0, because when y is infinity, e to the power y minus nu will reach infinity, and the exponential reach to infinity will be at a higher rate than linear rate of reaching infinity for y to the power 3 by 2. So that will be 0, and when y is 0, this will give 0. So we are left with, because this minus sign and that minus 1 makes it plus, 2 by root pi into 2 by 3 integral 0 to infinity y to the power 3 by 2 into e to the power y minus nu dy divided by e to the power y minus nu plus 1 whole square. So that is 4 by 3 root pi integral 0 to infinity y to the power 3 by 2 into e to the power y minus nu dy divided by e to the power y minus nu plus 1 whole square. This is f3 by 2 z, when n lambda cube is very large compared to 1. At this stage, we will make use of what we call Taylor's series expansion. Taylor's series expansion. Now, if fx is expanded about a, if fx is expanded about a, fx will be approximately fa plus f prime a, that is first differential of f at a, x minus a divided by 1 factorial plus f double prime a, that is second derivative, x minus a whole square divided by factorial 2, and so on. That is called Taylor series expansion. When we expand fx about a, so expanding y to the power 3 by 2 about nu will obtain y to the power 3 by 2 approximately as nu to the power 3 by 2 plus derivative of y to the power 3 by 2 at nu, that means 3 by 2 y to the power half will be nu to the power half, and y minus nu divided by 1 plus 3 by 2 into 1 by 2 into, now this y will be minus half, so nu to the power minus half y minus nu whole square divided by factorial 2, and so on. So y to the power 3 by 2 is approximated as nu to the power 3 by 2 plus 3 by 2 nu to the power half y minus nu plus 3 by 8 nu to the power minus half y minus nu square. So for this y to the power 3 by 2 here, we'll substitute from here, and then we'll obtain f 3 by 2z equal to 4 by 3 root pi integral 0 to infinity e to the power y minus nu divided by e to the power y minus nu plus 1 whole square into, for y to the power 3 by 2 we are writing now, nu to the power 3 by 2 plus 3 by 2 nu to the power half y minus nu plus 3 by 8 nu to the power minus half y minus nu whole square into dy. Now let y minus nu equal to t. Then we will write f 3 by 2z equal to 4 by 3 root pi integral, for y equal to 0 t will be minus nu, so minus nu, and for y equal to infinity t will be infinity, so minus nu to infinity, e to the power t, y minus nu is t, divided by e to the power t plus 1 whole square into nu to the power 3 by 2 plus 3 by 2 nu to the power half into t plus 3 by 8 nu to the power minus half into t square and so on into dt, because dy will be equal to dt. We can further write for the limits of integration, as we have from minus nu to infinity, that can be written as minus infinity to plus infinity minus integral from minus infinity to minus nu. Now this whole expression under red bracket, let's say we have substituted here, this is f3 by 2z, and what we are suggesting is we write that expression here and here also. Now the second term, or second integral, this one, will be of the order of e to the power minus nu, because this limit is minus infinity to minus nu. Exponential term is there, so this will be of the order of e to the power minus nu. So what we do is we write this f3 by 2z as 4 by 3 root pi integral minus infinity to plus infinity e to the power t divided by e to the power t plus 1 whole square nu to the power 3 by 2 plus 3 by 2 nu to the power half into t plus 3 by 8 nu to the power minus half into t square dt plus a term which is of the order of e to the power minus nu. Obviously, this second term is not going to be very important, because nu we have taken as, if you remember, log z, and log z will be mu by kt, and as t is very small, nu will be very large quantity. So e to the power minus nu, any term which is of the order of e to the power minus nu will be negligibly small. So now we write for f3 by 2z as 4 by 3 root pi under bracket I naught nu to the power 3 by 2 plus I1, let us take 3 by 2 I1 nu to the power half plus 3 by 8 I2 nu to the power minus half and so on. This first term comes from here, the second term is coming from this second term, and so on. Let's rewrite it. f3 by 2z equal to 4 by 3 root pi integral I naught nu to the power 3 by 2 plus 3 by 2 I1 nu to the power 3 by 2 nu to the power half plus 3 by 8 I2 nu to the power minus half, and other terms which we are neglecting. Now n may be 0, 1, 2, 3 and so on. In is minus infinity to plus infinity t to the power n e to the power t dt divided by e to the power t plus 1 whole square. You see, when n is 0, it is 1, t to the power n will be 1 for n equal to 0, and e to the power t dt divided by e to the power t plus 1 whole square. That we get from here, from the first term. Now when n is equal to 1, we get t into e to the power t dt. That t comes from here. So t into e to the power t dt divided by e to the power t plus 1 whole square into dt. So that way, so if you expand this, suppose we take this one, f 3 by 2 z, we write 4 by 3 root pi outside. The first term will be e to the power t into dt divided by e to the power t plus 1 whole square, integral minus infinity to plus infinity, and this nu to the power 3 by 2 is outside. So this is I naught plus, now the second term, we have 3 by 2 nu to the power half outside, and what we obtain is minus infinity to plus infinity t into e to the power t dt divided by e to the power t plus 1 whole square. So that is t equal to 1, n equal to 1. So I1 it is, which we have over here, plus if you take the third term, that is 3 by 8 nu to the power minus half, and what remains is minus infinity to plus infinity from this term, t square e to the power t dt divided by e to the power t plus 1 whole square. So that is I2, n equal to 2, so it is t to the power 2. So that is what IN are. If we look at this expression carefully, we find that apart from the factor t to the power n, the integrand is an even function of t, that you can check. Thus the integrand shall vanish for all odd n. So for all odd n, integrand will vanish. So it will give non-zero value only for even n. So for all odd n, integrand will vanish because apart from t to the power n, the integrand is an even function of t. So we examine this for even n. When n equal to 0, one can show that I naught will be equal to 1, and for n greater than 0, remember these are all even n. So for n greater than 0, this IN is equal to n minus 1 factorial. We are using the result again into 2n into 1 minus 2 to the power 1 minus n zeta n, where zeta n is Riemann zeta function, this Riemann zeta function is a tabulated function, and some of the values we can write zeta 2 is equal to pi square by 6. We are not interested in zeta 1, zeta 3, etc., because we are interested in even value of n only. So zeta 2 is pi square by 6. Zeta 4 is pi to the power 4 divided by 90. And zeta 6 is pi to the power 6 divided by 945, and so on. So when you substitute these values of I0, I1, I2, etc. in this equation, we will obtain f3 by 2 z equal to 4 by 3 root pi into nu to the power 3 by 2 I0, that is 1, plus nu to the power half into 3 by 2 I1 plus nu to the power minus half 3 by 8 I2, and so on, plus a term of the order of e to the power minus nu is equal to 4 by 3 root pi nu to the power 3 by 2 plus nu to the power half 3 by 2, but I1 is 0 because n is 1, so that is 0, plus nu to the power minus half 3 by 8, and I2, when you substitute the value of 2, we get twice into pi square by 6 plus other terms, and a term with order e to the power minus nu. So that is 4 by 3 root pi. Now nu is log z, so log z to the power 3 by 2 plus this will be log z to the power minus half divided by 8 pi square plus other terms plus a term of the order of e to the power minus nu. So this is f3 by 2 z. A graph of f3 by 2 z against z is shown in the figure. Now it is seen from this figure that z increases monotonically as n lambda cube increases. Also, for fixed n, that is particle density, z increases monotonically. For any given positive value of n lambda cube, the value of z can be found from this graph. We also know that this f3 by 2 z is z minus z square by 2 to the power 3 by 2 plus z cube by 3 to the power 3 by 2, and so on. So to a first approximation, when we take only the first term, f3 by 2 can be taken as z. So another fact is that z is equal to n lambda cube plus n lambda cube whole square divided by 2 to the power 3 by 2. So if we restrict to the first term, z is n lambda cube, f3 by 2 z is z if we restrict to the first term. So this equation can be written as f3 by 2 z equal to 4 by 3 root pi log z to the power 3 by 2 plus, you see, pi square by 8 divided by log z to the power half, and so on. So when we take f3 by 2 z equal to z and z equal to n lambda cube, we write from here n lambda cube equal to 4 by 3 root pi log of, this is under bracket, log of z to the power 3 by 2 plus, now this term can be written as 4 by 3 root pi, and here remember that this log z to the power half is in the denominator and we are approaching lower temperature. So suppose when we approach absolute zero, log z becomes so large that pi square by 8, 1 by log z under root can be neglected. So the second term can be neglected. This will be approaching 0. Log z, you see, log z is, if you remember, log z is mu by kt. And if t is approaching absolute 0, log z becomes very high, so that when log z is in the denominator, the term can be neglected. So we are left with n lambda cube equal to 4 by 3 root pi into log z to the power 3 by 2 when temperature reaches absolute 0. So in the neighborhood of absolute 0, n lambda cube, which can be written as n into h cube divided by 2 pi m kt to the power 3 by 2 is equal to approximately 4 by 3 root pi into log z to the power 3 by 2. Hence, if we write z equal to e to the power beta epsilon f, then from this equation, let's write for z, we will get log z to the power 3 by 2 equal to n 3 root pi divided by 4 into h cube divided by 2 pi m kt to the power 3 by 2. So when we write for log z, we'll get on the right hand side to the power 2 by 3. So we get n 3n by 4 root pi to the power 3 by 2, rather 2 by 3, and h square divided by 2 pi m kt. On simplification, this will be h cross square by 2m 6 pi square n to the power 2 by 3 divided by kt, where h cross is h by 2 pi, and that means z will be equal to exponential h cross square by 2m into 6 pi square n to the power 2 by 3 into beta. That beta is 1 by kt. So comparing these two, where we have written z equal to e to the power beta epsilon f, and this z which we have found from this expression, we get epsilon f equal to h cross square by 2m 6 pi square n to the power 2 by 3. This is epsilon f, and this epsilon f is called Fermi energy. So this is epsilon f Fermi energy. The physical significance of Fermi energy can be demonstrated if we consider average occupation number near absolute zero. So in the neighborhood of absolute zero, average occupation number NP bar will be 1 by e to the power beta epsilon p minus epsilon f plus 1, because what we have is 1 by e to the power beta, now e to the power alpha with a minus sign into e to the power beta epsilon p plus 1. Now e to the power minus alpha is z to the power minus 1, and we have taken z equal to e to the power beta epsilon f. So e to the power minus alpha is e to the power minus beta epsilon f. That's why this becomes beta epsilon p minus epsilon f plus 1. From this equation, now if epsilon p is less than epsilon f, then as t tends to 0, that means beta tends to infinity, the exponential in the denominator, that is e to the power, now we can write minus beta epsilon f minus epsilon p, because epsilon p is less than epsilon f. So beta is tending to infinity, so e to the power minus infinity, that will tend to 0. So in that case NP will be 1. Otherwise, say epsilon p is greater than epsilon f, then the exponential in the denominator e to the power epsilon p minus epsilon f divided by kt, where kt tends to 0, this term will tend to infinity. That means NP will be 0, NP bar will be 0. So we can summarize as NP bar in the neighborhood of temperature reaching absolute 0 is equal to 1 if epsilon P is less than epsilon F, and that will be 0 if epsilon P is greater than epsilon F. So all the states having energy less than Fermi energy will be occupied by one fermion, and all those states having energy greater than Fermi energy will not have any fermion in it. So those states will be empty. So remembering Pauli exclusion principle, which states that no two particles may be present in the same level, physical significance of the above formula can be understood. This formula: in the ground level of the system, the particles occupy the lowest possible levels and fill the levels up to the finite energy level epsilon F. So in the ground level, the particles start filling the states from lowest energy. So this will be filled, a particle here, another particle there, so and so on, and this will continue up to certain level. Say if this is epsilon F, then up to this the particles will be there in every state, one particle in every state, and beyond that all the energy states are empty. Thus epsilon F is simply the single particle energy level below which there are exactly capital N states, because total number of particles is capital N. So below this there are exactly capital N states. If we take the corresponding momentum as Pf, then epsilon F is equal to Pf square by 2m. That means in momentum space, the particles fill a sphere of radius Pf, the surface of which is called Fermi surface. Fermi surface. So Fermi surface is the surface of a sphere in momentum space up to which the particles are filled. Now this calculation for Fermi energy is for spinless Fermi gas. This is for spinless Fermi gas. However, if the particles have a spin, then for a given momentum P, there are For a given momentum P, there are 2s plus 1 single particle states. 2s plus 1 single particle states, all having the same energy epsilon P, all having the same energy epsilon P. So the equation for total particles, total number of particles, N must be modified, and that will be 2s plus 1 into V divided by 2 pi h cross whole cube into 4 pi by 3 Pf cube, and the expression for Fermi energy changes, and that becomes epsilon F equal to h cross square by 2m into 6 pi square n divided by 2s plus 1 to the power 2 by 3. So for particles with spin s, the Fermi energy is given by this equation. We will stop here for today, and next day we will find other thermodynamic quantities of an ideal Fermi gas.